So good morning dear students. Today we can discuss about some important basic topics that is coming under acid and base titrations. So which are the topic we are going to discuss is first one is the relative strength of acids and bases. And second one is law of mass action. Then the common ion effects, Henderson-Hasselbalch equation. In case of relative strength of acids and bases, what do you mean by stronger acids? Stronger acids are those that loses their protons more easily than others. Similarly, a stronger base is those that hold their protons more strongly than the others. An acid is strong if it is completely ionizes in water, and this can be explained by the reaction of hydrogen chloride with water. And during the reaction of hydrogen chloride with water, the hydrogen chloride will completely ionizes in water, and this hydrogen chloride acts as an acid while the water acts as a base. And here is the reaction. HCl in aqueous, it is acid, is reacted with water, that is base, will give Cl minus and H3O plus. Cl minus is the base and H3O plus hydronium ion is the acid. And the reverse reaction occurs only to an extremely small extent because the reaction completely goes to the right path because the hydrochloric acid ionizes completely, and hence it is a strong acid. And next in detail we can discuss what is the relative strength of the acid, or what is the strength of acids or acidity. The strength of an acid depends on its ability to transfer its proton towards a base to form a conjugate base. And in case of a monoprotic acid, that is HA, when it is dissolved in water, it transfers its proton to a water, and this water acts as a Bronsted base, and while transferring this proton to a water they will form a hydronium ion, that is H3O plus, and a conjugate base. And here we have discussed the reaction clearly, that is HA, which is a monoprotic acid, on dissolving in the water, and this water acts as a Bronsted base. They will form a hydronium ion, that is H3O plus and A minus. This A minus is a conjugate base. For simplifying our discussion, we can take our hydronium ion is equal to the H plus. This we can write the above equation as HA plus H2O gives H plus plus A minus. And this equation represents the dissociation of acid HA into H plus ion and A minus ion. By applying the law of mass action, the law of mass action we can discuss in the next topic. By applying the law of mass action to this acid dissociation equilibrium, we can write the above reaction equation as Ka is equal to concentration of H plus into concentration of A minus divided by concentration of HA. And here the Ka is called acid dissociation constant, and HA is an acid. And from this it is evident that the concentration of H plus depends on the value of Ka. That is, the value of Ka for a particular acid is a measure of its acid strength or acidity. So the relative acidity of a particular compound, or the measurement of the acidity of a particular compound, can be determined from the value of Ka. That is the acid dissociation constant. And next is the relative strength of the base. According to Arrhenius concept, we have discussed that base is a substance which produces OH ions in the aqueous solution. So the basic property of such substances can be explained easily in terms of hydroxyl ions. Let us consider a base, that is BOH, whose dissociation can be represented as BOH gives B plus and OH minus. By applying the law of mass action to this equation, we can write it as Kb is equal to concentration of B plus into concentration of OH minus divided by concentration of BOH. And here this Kb is called base dissociation constant or base ionization constant. As like the acid ionization constant, the strength of base is defined as the concentration of OH ions in its aqueous solution at a given temperature. From the previous equilibrium expression equation, it is clear that the concentration of OH ions depends on its Kb value, that is base ionization constant value. Therefore, the value of Kb for a certain base is a measure of the basic strength, or it is a measure of the basicity. Next topic is the law of mass action. So we have previously discussed in the relative strength of acids and bases. To certain equations we are applying the law of mass action, and by applying this we are identifying the acid constant as well as base constant. So we have to know in detail what is this law of mass action. So there are two chemists who were Norwegian origin, that is Guldberg and Wage, in 1867. They postulated a generalization called as law of mass action, and according to this postulation, they states that the rate of chemical reaction is proportional to the active masses on the reactants. And what do I mean by these active masses? This active masses is meant that it is a molar concentration, and it is expressed by enclosing the formula of the substance in a square bracket. This can be easily explained by the reaction, that is CO, carbon monoxide, react with the 3H2O to give CH4, that is methane, plus water. And here, according to law of mass action, we can write Kc. The equilibrium constant can be written as the concentration of CH4 into concentration of H2O divided by concentration of CO into concentration of H2 raised to 3. That is, the rate of chemical reaction is proportional to the active masses of the reactants. And here Kc is the equilibrium constant. And if you are taking in general reaction, that is A plus BB gives CC plus DD, where capital A, B, C, D denotes the reactants and products, and A, B, C, D are the coefficients in the balanced chemical equation. Based upon the law of mass action, we can write the dissociation constant Kc is equal to concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B, where the numerator is the product's concentration and the denominator is the reactant concentration. So that's all regarding the law of mass action. Hence, from the law of mass action, it is a relation that states that the values of equilibrium constant expression K are constant for a particular reaction at a given temperature, whatever equilibrium concentrations are substituted. Next is the common ion effects. In common ion effects, the concentration of a particular ion in an ionic reaction can be increased by addition of a compound which produces that ion upon dissociation. And the particular ion is thus derived from the compound which can be already in the solution. Also, they can be obtained from the added reagent, and hence we call the name as common ion. In the solution of an electrolyte in water, there exists an equilibrium between the ions and undissociated molecules, to which the law of mass action can be applied. We can explain the common ion effect by considering the dissociation of electrolyte equation, that is AB is equal to A plus B minus. According to law of mass action, dissociation constant K is equal to concentration of A raised to plus into concentration of B raised to N divided by concentration of AB. And into this solution, and another electrolyte or salt is added, that is having a common ion of A plus B, and when this is added, it will result in increase in the concentration of the A plus ion and B minus ion, in order that the K may remain the same. When the concentration of A plus and B minus is increasing, so there is no need of dissociation of AB. This indicates that the concentration of AB must eventually increases. In other words, The degree of dissociation of electrolyte is suppressed by the addition of another electrolyte containing common ion. From the above reaction, that is, the AB dissociate to give A plus and B minus, and we are adding additionally an electrolyte that is having A and B, which results in the automatic increase in the concentration of A plus ion and B minus ion. As the concentration of A plus and B minus are increasing, there is no need of this AB to dissociate to give A plus and B minus, and hence the dissociation of AB will stop there. And this addition of the electrolyte that is having a common ion similar to that of the product results in the stop of the dissociation of the reactant, and this ion is called a common ion, and this effect is called a common ion effect. Hence, the common ion affects the shift in an ionic equilibrium caused by the addition of a solute that provides an ion that takes part in the equilibrium. And this can also be explained by the example of the dissociation of an electrolyte ammonium hydroxide is diminished by the addition of ammonium chloride, which furnishes the common ion, that is NH4 ion. And next is the pH of a solution. We already know what is pH. It is defined as a negative logarithm of molar hydrogen ion concentration, and this can be mathematically expressed as pH is equal to negative log of H plus ion concentration, where H plus is the concentration of hydrogen ions in mole per liter, and in case of a neutral solution whose hydrogen ion concentration is 25 degrees Celsius, it is 1 into 10 raised to minus 7 molar, and it is having a pH of 7. If in case of acidic solution, hydrogen ion concentration is greater than that of 1 into 10 raised to minus 7 mole, so the pH is less than 7. And in case of basic solution, the pH will be greater than 7. How we can determine the pH of a solution? The pH of a solution can be determined accurately by two methods. First method is a electrometric method, that is potentiometric method, and second method is a calorimetric method. In potentiometric method, it is more accurate and is using an ultimate standard of hydrogen ion concentration. It is mainly applied for the means of potentiometric measurements and used along with a pH meter. Here the hydrogen ion concentration of a solution can be determined electrometrically like potentiometrically by measuring the potential difference set up between the electrode immersed in the solution and a standard electrode of non-potential. And the standard electrode example is a standard hydrogen electrode. And next is the calorimetric method. It is also based on the use of certain reagents which alter the color in accordance with the hydrogen ion concentration. And these reagents such as litmus paper, which contains azolitmic acid with a red undissociated molecules yielding a blue anions, and this is an example for the acid base indicators. Next is the important part, that is Henderson-Hasselbalch equation. The pH of a buffer solution is related to pK of the buffer acid and the log of the ratio of buffering species, and this relationship is described by the Henderson-Hasselbalch equation, and this can be derived from the ionization constant expression for the weak acid. For the weak acid, the ionization constant expression is equal to pH is equal to pK plus log concentration of conjugate base divided by acid, concentration of acid. This equation relates the pH of a buffer for different concentration of a conjugate acids and base, and hence it is also known as Henderson-Hasselbalch equation. Now, considering case of weak acid, the weak acid is slightly dissociated and its dissociation is further depressed by the addition of the salt, that is N plus and A minus, and this depression of the dissociation by the addition of a salt that is having a common ion is called common ion effect. As a result of this common ion effect, the equilibrium concentration of the unionized acid is nearly equal to the initial concentration of the acid. And the equilibrium concentration of A minus is presumed to be equal to the initial concentration of salt added. Since it is completely dissociated, we can write the equation as concentration of H plus is equal to Ka into concentration of acid divided by salt, where the concentration of acid is the initial concentration of the added acid and concentration of salt is that of the salt used. If you take a negative logarithm into this, we will get the equation as negative log concentration of H plus is equal to negative log of Ka minus log concentration of acid divided by concentration of salt. We already know the negative log of H plus is called pH and log Ka is called pKa. And by substituting this on the previous equation, we get pH is equal to pK minus log concentration of acid divided by concentration of salt, which can be written as pKa pH is equal to pK plus log vice versa, that is salt divided by acid, because we are changing the negative sign here. We are taking the salt on the numerator and the acid on the denominator. Hence the pH is equal to pKa plus log concentration of salt divided by concentration of acid. And this relationship is called the Henderson-Hasselbalch equation or simply Henderson equation. Similarly, we can identify the Henderson equation for a basic buffer and the same steps, and we will get finally the equation as POH is equal to pKa plus log concentration of salt divided by concentration of base. Thank you.